let's start chapter 11 now. Um, Significance of derivative. Chapter 11. Significance of the derivative. Well, here's our first definition. This is something everyone here should know, but we are going to define it anyway. Let f be a function with a set A, which is a subset of domain of f. Domain f. Okay. In that case, I am going to call x is the maximum point or maximum of f in A if f of x is greater than or equal to f of y for every y in A. Okay. Okay, I missed a small point. X should be in A. X in A is the maximum of A if this is if it is bigger than everything. Similarly, X in A is called the minimum, is the minimum of f in A if f of x is smaller than or equal to f of y for every y in A. Right? This is nothing new. You have seen this like always since a very long time, and it's the usual stuff, right? In that case, we can go to theorem 1. Theorem 1. Let f be a function on A to B, on A B, if f has a maximum or minimum at x and f is differentiable at x, f is differentiable at x, then f prime of x is equal to 0. I'm not going to say that f should be continuous everywhere or it should be differentiable everywhere, nothing of that sort. If x is a minimum and it is differentiable at x, then your derivative is 0. We have no claims about any other point, right? And I'm going to prove it for, let's say, maximum. Proof for minimum follows exactly similarly. Proving for maximum, proving for maximum, similar proof for minimum, right? And how do we show this? Well, if it's a maximum, my function is going to look something like this, right? This is my point x. I'm not saying the function is going to be continuous everywhere, or whatever. My AB might be here. AB, it might have a jump here. I don't know. Something. Doesn't matter. But at x, my function is continuous, right? Function is not just continuous, it's actually differentiable. So if I look at the secant lines from the left and the secant lines from the right, oops. Okay. This is so hard. Okay, whatever. Okay, this is my final attempt. Whatever happens, happens. Okay, if we look at the secant lines from the left and the secant lines from the right, then we get that if h is greater than 0, then we'll limit h goes to 0, f of x plus h minus f of x over h is smaller than or equal to 0. If h is smaller than 0, then limit h goes to 0, f of x plus h minus f of x over h is greater than or equal to 0. Right? Because now I'm taking some point smaller and then going up. Right? But the derivative exists. Therefore, limit h goes to 0 from the when h is smaller than 0 should be equal to the limit h goes to 0 when h is greater than 0. So f of x plus h minus f of x over h is both smaller than or equal to 0 and greater than or equal to 0. Right? Therefore, limit h goes to 0, f of x plus h minus f of x over h is exactly equal to 0. Okay? The same exact result holds for minimum, right? Where the proof would be, oh, the other side limit is going to be less than or equal to 0 or greater than or equal to 0. Okay? Then we'll define another thing. Definition. A point of f is a critical point. A point x is a critical point of f if f prime of x is equal to 0. Okay, so this is what I'm going to call the critical point, and the value of f of x is called critical value. Okay, so sometimes people include the endpoints or where the function is not differentiable to have critical points in critical points, but in our case we will not be referring to those as critical points or critical values. Those we'll consider it separately. Okay, so example. Okay, never mind. This is plain. Let me stop this one here. I'll do the examples and further results in the next one.